Welcome to an intro to double integrals in polar coordinates. Sometimes a double integral is much easier to evaluate using polar coordinates. This is especially true if the region of integration can be easily defined using a polar equation. So because we're going to be converting from rectangular to polar coordinates, it is important that we remember the following equations. So you may want to copy these into your notes. If f of x is continuous on a polar region defined as given here, then we can rewrite a double integral in rectangular form into polar form as we see here. And there's a couple important things to notice here. First, our function f of x, y is going to be converted into a polar equation as we see here. The way we do this is we replace x with r cosine theta and y with r sine theta. And sometimes the function is written like this to represent polar form, and sometimes it's just written as f of r theta. And there's one more very important thing to notice. Differential A is replaced with r dr d theta. So there's an extra factor of r in the integrand when we convert from rectangular to polar form. And we'll take a look at why that is in just a minute. Let's take a look at these two graphs below. Notice in rectangular form, we were determining the volume of these boxes, where the bases were squares. Well, in polar form, we still want to determine the volume of these boxes, but now the bases aren't quite rectangular, so it's going to take a modification of the formula to determine differential A. Let's take a look at that. So again, in rectangular form, we determined that differential A was equal to dx times dy, because this represented the area of a base, which was a square, or a rectangle. Now if we take a look at the base of one of those boxes in polar form, it's going to look more like this. So delta theta would be the change in the angle, as we see here. This shorter radius would be r1, and the longer radius would be r2. So to determine the length of this piece here and this piece here, we'd actually have to use the arc length formula, which states that arc length s is equal to r times theta. So this length here would be r1 theta, and this would be r2 theta. And the length of this segment here would be delta r, which we can set equal to r2 minus r1. Now, of course, as we let the number of boxes approach infinity, r1 is going to be approximately equal to r2, which we'll let equal r. So from here we can say that delta A, or the change in the area, would be approximately equal to r times delta theta, again because these are all approximately equal to each other, times delta r. So now you can see where this extra factor of r comes from. Go back up here and look at differential A. It's equal to r dr d theta. Well, here's the extra factor of r. And then again, as the number of boxes approaches infinity, delta theta is approximately equal to differential theta, and delta r is approximately equal to differential r. So hopefully this rough outline helps you understand why when converting to polar form we do have this extra factor of r in the integrand. Let's go and take a look at an example. We want to determine the volume of the solid below the surface given by f of xy above the xy plane over the region bounded by x squared plus y squared equals 1 and x squared plus y squared equals 4. Well, the first thing we should recognize here is that these two are circles, one with radius 1 and another with radius 2, as we see graphed here in red. So our region of integration is the region between these two circles. This is a great example of when it'd be easier to evaluate this using polar coordinates. And here you can see the solid, and I've traced the region of integration in red in the xy plane. So let's see if we can set this up. The first thing we're going to do is rewrite the function as a polar equation. Let's first write this as 4 minus the quantity x squared plus y squared. The reason that's helpful is remember that x squared plus y squared is equal to r squared. So we can rewrite this in polar form as 4 minus r squared. Now see if we can set up our double integral. Our function is now 4 minus r squared. Remember, now we're going to have an extra factor of r and then dr d theta. Well, remember, r stands for the radius. Well, this circle here would be r equals 1, and this circle here would be r equals 2. So the limits of integration for r would just be from 1 to 2. And then because we want one complete revolution around this circle, the limits of integration for theta will be from 0 to 2 pi. Let's go and distribute the r. So we'll have 4r minus r to the third dr d theta. Let's go ahead and finish this on the next slide. So we'll have 4 times r squared over 2 minus r to the fourth over 4. Let's go ahead and clean this up a little bit. So we'll have 2r squared minus 1/4 r to the fourth. So when r is 2, looks like we'll have 8 minus, this is going to be 16 divided by 4, that's 4. And then when r is 1, we'll have 2 minus 1/4. So we'll have 4 minus 1 3/4 or 7/4. That's going to give us 9/4. Now we'll integrate with respect to theta. That's going to be 9/4 theta. So when theta is 2 pi, we'll have 2 pi and then minus 0. It's going to give us 9/2 pi. So the volume of the solid over this region in orange would be 9/2 pi. Let's take a look at one more example. Here we want to determine the volume of this function over the region x squared plus y squared is less than or equal to 4 in the first octant. So we have a circle with radius 2, but we only want it in the first octant, so it's going to be this region here. Now that we have a region of integration, the first thing we should do is convert this to a polar equation. So if we rewrite this as the square root of 9 minus the quantity x squared plus y squared, we can replace x squared plus y squared with r squared. So our double integral, the function is going to be the square root of 9 minus r squared, and then don't forget our extra factor of r, and then dr d theta. So let's determine what r would be. Well, this is a circle with radius 2, so r is going to be from 0 to 2. But now because we're in the first octant, theta is only going to be from 0 to pi over 2. And now we're ready to go. This is going to require u substitution, though. We would have u equals 9 minus r squared. So du is going to be negative 2r dr. So that tells us that we can replace r dr with negative 1/2 du. So we have negative 1/2 du, and this would just be u to the 1/2. So we'll have negative 1/2. This would be u to the 3/2 divided by 3/2, or times 2/3. And u is really 9 minus r squared. This simplifies here to negative 1/3. Let's finish this on the next slide. So when r is equal to 2, we're going to have 9 minus 4. It's going to be 5 to the 3/2. And then when r is 0, we're going to have 9 to the 3/2. Let's go and distribute here. Negative 1/3 times negative 9 to the 3/2, that's going to give us a positive 9. Then we'll have minus, and here we'd have 5 square root 5 all over 3. This is just a constant. So we're going to have 9 minus 5 square root 5 over 3 theta times pi over 2. Let's go ahead and get a common denominator here. So the denominator would be 6. Then we'd have 27 minus 5 square root 5 times pi. And we'll leave it like that. We'll take a look at some more examples in the next video. Thank you for watching.